There are two questions given here, but in exam you can choose either first one or second one. Now let us discuss one by one. First we'll take question A. Here the questions define the term focal length of a mirror with the help of a ray diagram and update the relationship between focal length and the radius of curvature. Now let us take the ray diagram. So here we have the line and the convex mirror we are going to consider here. So let us take the point P here and the light ray incident on the mirror. So this is center of curvature and let us take M here. We'll consider one more ray. This is F and the perpendicular is MD. So now the angle theta and here also theta. So this will be 2 theta and again here we have the angle theta. So now let us define the term focal length of a mirror. So focal length of a mirror is nothing but the distance between the focus and the pole of a mirror. So this is focal length of a mirror. Now we know that the light ray parallel to the principal axis striking the mirror at point M and C is the center of curvature at the mirror. So CM will be normal to the mirror. And theta be the angle of incidence and MD be the perpendicular from M to the parallel axis. Now we are going to write the angle MCP which is equal to theta and angle MFP which is equal to 2 theta. And now we can write tan theta which is equal to MD by CD and tan theta equal to MD by FD. For paraxial rays, theta is very small, so tan theta is approximately equal to theta and tan 2 theta is approximately equal to 2 theta. So we can write MD by FD which is equal to 2 times of MD by CD, or we can say FD equal to CD by 2. So now from this, we can say that for small theta, point D is very close to point P. Now we can write FD which is equal to F and CD equal to R. So if we substitute the values here, we get F is equal to R by 2. So this is the relationship between focal length and radius of curvature. Now we'll discuss question B. See here the question is calculate the angle of emergence E of the ray of light incident normally on the face AC of a glass prism ABC of refractive index is √3, and they're asking how will the angle of emergence change qualitatively if the ray of light emerges from the prism into a liquid of refractive index 1.3 instead of air. Now let us take the given figure A, B, C. So here they are saying the light incident normally on the face AC. So here the incident on face AC and directly passes through AB. So here we are getting angle of emergence and it forms the angle 30 degree here and 60 degree. So this is 90 degree. So this will be 60 degree. Again this is 30 degree. Right. So as light rays incident on the face AC, it goes anti-evated and strike the face AB. At face AB, the angle of incidence is 30 degree. So now we are going to apply Snell's law of refractive surface AB. So we get sine 30 degree divided by sine E which is equal to NA by NG. So now we get sine E which is equal to √3 by 1 into 1 by 2. So we have sine E which is equal to √3 by 2 is nothing but sine 60 degree. So the value of A is 60 degree here. How will the angle of emergence change qualitatively if the ray of light emerges from the prism into a liquid of refractive index 1.3 instead of air? So obviously it will bend away from the normal by a smaller extent as compared to air. So the angle of emergence will be less than 60 degree. Now let us discuss Our question, in this we have question A. The questions define the term resolving power of a telescope. How will the resolving power be affected with the increase in wavelength of light used, diameter of the objective lens? And they're asking us to justify our answer. So now in this case, the resolving power of a telescope is defined as the reciprocal of the smallest angular separation between two-point object whose images can just be resolved by telescope. So this resolving power is defined as d by 1.22 lambda. So the first thing is they are asking wavelength of light used. Okay. So as wavelength lambda increases, the resolving power Rp decreases because they are inversely proportional. Now the second case, diameter of the objective lens. So when the diameter of the objective lens increases, so Rp also increases because they are directly proportional. Right. Now the second question is B. Here the screen is placed 80 cm from an object. The image of the object on the screen is formed by a convex lens placed between them at two different locations separated by a distance of 20 cm. Now they are asking us to determine the focal length of the lens. So the distance between the two lenses 20 cm. So this is 20 cm and the screen is placed 80 cm from an object. So we'll place the screen here somewhere. So the screen is placed 80 cm from an object. So here let us take this distance is A and this distance is B. So this is 20 and this is 80. Okay. Now based on the information given, we got the position of the lens. By lens formula, we can write 1 by V minus 1 by U, which is equal to 1 by F. So here we have 80 minus A. The V is 80 minus A plus 1 by A, which is equal to 1 by 60 minus A plus 1 by 20 plus A. So if we simplify this, we get A into 80 minus A, which is equal to A plus 20 into 60 minus A. Again we get 80 minus A square, which is equal to 40A plus 1200 minus A square. So again if we solve for A, we get the value of A as 30 centimeter. So we get 1 by F, which is equal to 1 by 50 plus 1 by 30. So if we simplify this, we get 8 by 150. So F is equal to 150 by 8 centimeter. So the value is 18.75 centimeter. Now the question is, what is the focal length of the lens? So the focal length of the lens is nothing but 18.75 centimeter.